We're continuing section 7.4 on marginal distributions and independence. Definition 7.4.3. Let x and y be jointly distributed continuous random variables with joint probability density function f of xy. The marginal probability density function of x is f sub x of x, and it is the integral from minus infinity to infinity of the joint density function, dy. Now, the marginal probability density function of y, f sub y of y, is, well, it's the integral from minus infinity to infinity of the density function dx. So what happens when you integrate with respect to one variable only? Well, that variable disappears. So the x will then disappear, and what we'll be left with is a function of y in this integral, and opposite here, the y will disappear, and what will be left is a function of x. And that is the first remark, that the act of finding a marginal density function is often called integrating out, because the variable disappears, integrating out each variable. So here I would be integrating out y and have x remaining. Here I'm integrating out x and I have y remaining. And the second remark is that integrating from minus infinity to infinity simply means integrating over all possible values of each of the variables. So let's do example 7.4.2, and we'll put this into practice. So the joint probability density function for two continuous random variables x and y is given here. We're asked to find the two marginal density functions in part A, and then in part B we're asked to use them to calculate probability. So to find these, well, let's start by taking a look at the support that we have here. And so we have, this is not at all what I wanted. Let's add some axes here. So here's my x and the y. And if we have x going from 0 to 1, so we have x going from 0 to 1, let's put the 1 here, and y goes from 0 to 1 minus x, so 1 minus x is the line here, that's y is equal to 1 minus x. That's the line that has intercepts of 1 and 1 on both axes, and so this is the area where our density is non-zero. And so if we want to integrate here, we want to integrate to get the x marginal density function. So f sub x of x is the integral from minus infinity to infinity of f of x y dy. So that means I want to integrate over all possible y values. Well, let's take a look. For a given x, value, right, a given x value, y goes from 0 to 1 minus x. So that integral is equivalent to the integral from 0 to 1 minus x, because outside of that interval everything is 0. And if we integrated on the parts where we have a 0 density, we're just going to get 0. So the integral from 1 minus x of the density function, so that's 2x plus 4y, and then we're integrating with respect to y. So then it's now just, it's just an integral. So we're going to anti-differentiate, so we're going to get 2xy plus 2y squared, and we're running that from 0 to 1 minus x. So we get here 2x times 1 minus x plus 2 times 1 minus x squared minus 0 plus 0. So that, if we simplify, what are we going to get here? 2x minus 2x squared plus 2 times 1 minus 2x plus x squared. And so those 2x squareds are going to cancel. I have 2 times 1 is 2, and then this 2x, and I have a minus 4x, so 2 minus 2x. Now that is not the full answer. That is only the part where the density is non-zero. So to give a full and complete answer, we need to write the full density function with the support and where the density is 0. So we actually have f sub x of x is 2 minus 2x, And that was possible, or that was valid on 0 is less than or equal to x is less than or equal to 1, and the density is 0 otherwise. So there is our full answer for the marginal density of x. Now we want the density of y as well. We want the marginal for y, and so we're going to flip things around. We want to integrate out the y, which means, no, we did that. We want to integrate out the x. So f sub y of y is going to be the integral from minus infinity to infinity of f of xy, this time dx. So for a given y value, we want to integrate over all possible x values. So we're going to turn this region into a region of the other type. So if we go for a given y value, x goes from 0 to, well, this is the line x is equal to 1 minus y. And so that integral becomes the integral from 0 to 1 minus y of the density function, 2x plus 4y dx. So I just want to make sure that we're cognizant of what we just did here, right? We just rewrote that as a region of type 2 instead of type 1, right? So our new region, or our new way of describing the region, is 0 is less than or equal to y is less than or equal to 1, and 0 is less than or equal to x is less than or equal to 1 minus y. That is what we just did. Now, we're just going to integrate here the same way, but this is now an integral with respect to x, and so we're going to get 2x squared. No, we're not. The 2 disappears. We get x squared plus 4xy, and that is the antiderivative that's run from 0 to 1 minus y, and so 1 minus y all squared plus 4 times 1 minus y times y minus 0. And so we're going to simplify here, 1 minus 2y plus y squared, and then we get plus 4y minus 4y squared, and that finally gives us 1 minus 2y plus 4y, so 1 plus 2y minus 3y squared. And again, that's not the complete answer, that's just where that density is non-zero, so we have to write the full answer. F sub y of y is, it's got two parts. It's got this 1 plus 2y minus 3y squared, and that's valid from 0 to 1. So on 0 is less than or equal to y is less than or equal to 1, and then the density is 0 elsewhere or otherwise. So that's the first part. Those are the two marginals. Now let's look at part B, where we're asked to use one of them to find a probability. So this says, set up the integral or integrals required to find the probability that 1/4 is less than y is less than 3/4 in the following 3 ways. And then we're asked to actually evaluate it by the third method. So the first is, if we didn't know about marginals, we would just do this as a double integral over an appropriate region D. So let's do that. Let's find our region D and set up the integral. So here is the original support that I'm just sort of recopying from above. So we had from 1 to 1, and this was the line y is equal to 1 minus x, or x is equal to 1 minus y. I want y to go from 1/4, so 1/4, to 3/4 on the y-axis. And so I want this region here. The probability that I'm looking for corresponds to the area of that region, not the area, but the density integrated over that region. And so as a double integral, that region is, well, so the probability of 1/4 is less than y is less than 3/4 is the double integral over, and y is going from 1/4 to 3/4, so 1/4 to 3/4, and x is going from 0 to 1 minus y of the density function, so 2x plus 4y, and we've just done this as dx dy. So that is the answer to number 1, but I want to take a second here and take a look at that inner integral. This inner integral right here. That integral is exactly, in fact, why don't I actually write it? That inner integral right here, that is exactly the integral that we did up here. Right? That is exactly the same integral. That is the integral that you need to do to get the marginal. This is exactly the definition of f sub y of y, where that density is non-negative. Non-zero, I should say. So that means, right, that however we slice it, we're really just doing the same thing in different steps. So if we want to integrate the density function, well, the integral that we're going to have is the integral of this. And so that number 2 is actually, it's really, really quick. Number 2 is the integral, or the probability of 1/4 is less than y is less than 3/4. Now it's the integral from 1/4 to 3/4 of the marginal. That's what we would do with a single variable to find probability. And so we do the exact same thing with the marginal density. And that is, well, that's the integral from 1/4 to 3/4 of the integral that we just found, the antiderivative that we just found up here. So of 1 plus 2y minus 3y squared dy. So that's the answer to 2, setting that up by integrating the marginal density function. And then number 3 is, well, number 3 is really just a bit of a review from your first probability course, the cumulative distribution function, capital F sub y of y. How do we find that? Well, we integrate this. So this is, I mean, it's going to be the exact same thing. Right here, you would have to find an antiderivative and do top minus bottom. Well, the antiderivative that we're looking for is exactly that cumulative distribution function. So let's go and do that. So the third one here is the cumulative distribution function, capital F sub y of y, is defined as the integral from minus infinity to y of f sub y of t dt, right? It's important to get all of our variables aligned and correct. This is the capital Y, that's the random variable. This is the y, that is the variable here, and t is just a dummy variable, which means we want to integrate here. So we're going to integrate now. Again, this means all possible values, but we know that y is, or the density is 0 below 0. So that's the integral from 0 to y of this marginal function with a dummy variable of t. So that's 1 plus 2t minus 3t squared dt. So we're going to anti-differentiate this and run this from 0 to y. So the antiderivative that we want is t plus t squared minus t cubed. Oh, that's really nice. From 0 to y, or y plus y squared minus y cubed minus 0. But again, this is not the final answer. For the cumulative distribution function, you really need to write down the full function with its full values on all of the intervals. So that is, right, that function is 0, and 0 before we get to, the y value of 0. So that's 0 for y is less than 0. It is this function, y plus y squared minus y cubed, on 0 is less than or equal to y is less than or equal to 1. And then once you get past there, you've accumulated the full probability of 1, and that is for y is greater than 1. So there's the full CDF. And now if we want to calculate the probability, which is what we were after from the beginning, probability that 1/4 is less than y is less than 3/4, well, using the definition of the CDF, that is exactly f of 3/4 minus f of 1/4, which you notice is exactly what you would be doing if you integrated over here, right? That's an antiderivative evaluated at the top minus an antiderivative evaluated at the bottom. It's all the same thing, just packaged and labeled in a different way, but it's important for you to understand how these things all fit together. And so the last thing that we want to do is actually plug these numbers in. So we're getting 3/4 plus 3/4 squared minus 3/4 cubed minus, and then the same thing, we're going to plug in 1/4. So 1/4 plus 1/4 squared minus 1/4 cubed, and that is a long fraction calculation that I've done for you off screen and got 19/32.